Now I want to show you an example of calculating average rate of change of the same function over different intervals. So here's an example. Find the average rate of change of the function f of x over intervals of the form a plus h. So I will be using the other formula for the average rate of change, where a is chosen to be 1, a equals 1, but the h takes several values. So I remind you, h is length of that interval, and I want my h to equal 9, and then make it equal 1, and then make it 0.1, and then 0.01, and then 0.001. As you can see, I take several values for h that become smaller and smaller. Eventually, I will make the limit as h approaches 0. So, and now let's do these calculations. Obviously, every choice of h will make a different calculation of average rate of change. So it will be like 1, 2, 3, 4, 5 separate calculations. So calculation number 1. Take a equal 1 and h equal 9. So first of all, what is the interval in this case? The function will always be the same. So I want f of x to be the same, and I want it to be x squared plus 3x and minus 1. And the intervals will be different. So first a equals 1 and h equals 9. That makes the interval from a to a plus h. It makes an interval from 1 to 1 plus 9. 1 plus 9 is 10. So we're talking about calculating average rate of change of this function over this interval. And then average rate of change equals f of b, which is f of 10, or f of a plus h minus f of a, and that is f of 1. So once again, I want to remind you this formula over h. So f of a plus h minus f of a over h. So it will be f of 10 minus f of 1 divided by h value, which is 9. Now f of 10 is quite easy to calculate just by plugging it in, so it will be 10 squared is 100, plus 3 times 10, 130, minus 1 is 129, minus, now plugging 1 is also easy, 1 plus 3 is 4, minus 1 is again 3, so 129 minus 3, all of that over 9, which makes 126 over 9, which is 14. So it happens to be integer number 14. In fact, very often average rate of change is not integer because it is calculated as a fraction, but if we are lucky, so it will end up an integer number. That was the first calculation. Now the second calculation. I want to repeat all this calculation with a equals 1 and h equal 1 as well. So I make h, every time I make h smaller. So h equals 1. Now the interval in question will be from 1 to 1 plus 1. And 1 plus 1 is 2. So from 1 to 2. And again, average rate of change can be calculated as f of a plus h, which is 2, so f of 2 minus f of 1 over 1, because h equals 1. Again, plugging in 2 is not hard, so 2 squared is 4, plus 3 times 2 is 6, 4 plus 6 is 10, minus 1 is 9, so we have 9. We have 9 minus f of 1 already calculated, it's a 3, over 1, the answer is 6. So, as you can see, the average rate of change goes down. The question is, how far does it go down? Would it go down to 0 eventually, or maybe stop somewhere? We cannot answer this question until we do more calculations. So I want to repeat this calculation 3 more times. For h equals 0.1, for h equals 0.01, and for h equals 0.001. So the third time I do it for a equals 1 and h equals 0.1, which means in this case it will be interval with lengths only 1/10 of the unit. So it will be interval from 1, a is 1, and a plus h is now 1.1. So this is a pretty tiny interval. And now I'm calculating the average rate of change over this tiny interval. So average rate of change equals f of 1.1 minus f of 1 over 0.1. And now, of course, plugging in 1.1 in this formula is not easy, like you cannot do it manually, so I have to use calculator. And I will be using table feature because I will plug in many different values into the same function, x squared plus 3x minus 1. So, x squared plus 3x minus 1. So I want to plug in 1.1. And the answer is 3.51. 3.51. Now I subtract f of 1. F of 1 I already calculated, it's 3 over 0.1. Now 3.51 minus 3 is just 0.51. And 0.51 divided by 0.1 is like multiplying times 10, so we ended up 5.1. Okay, so 5.1. Now like I said, let's repeat this calculation 2 more times. So fourth time it will be for a equals 1 and h equals 0.0. Once again, our interval will now be a to a plus h. Since h is so small, so the interval is extremely small. So it's a 1 to 1.01. So the length of this interval, which is h, is just 1/100th. Let's calculate the average rate of change for this small interval, for this tiny interval. It will now be f of a plus h, which is f of 1.01 minus f of 1 over 0.01. Again, I'm plugging in 1.01 into this function. And the answer is 3.0501. So 3.0501 minus, again, f of 1 is 3 and over 0.01. So the answer is, well, the answer is 0.0501, and then when you divide by 0.01, it's like multiplying times 100. So this period becomes here, so it's 5.01. Now it's quite clear already that the values of the average rate of change don't really go all the way down to 0. They actually approach 5, because from 14 to 6 to 5, and then it becomes 5.1, and then the next step it becomes 5.01. So you may expect that the following step will be even closer to 5, and therefore the overall the values of the average rate of change approach 5. But just to make it more sure, I want to repeat this calculation one more time for h equals 0.0001, 1/1000th for a really tiny interval. And this is what I will do one more time. So the fifth calculation, or the fifth run of this numerical experiment. By the way, calculations like this are often called numerical experiments. They are similar to experiments in natural sciences like in physics or chemistry. So in mathematics we do similar things. So let us repeat the same calculation with a equals 1 and h equals 0.01, 0.001, 1/1000. Now in this run we have the interval from 1 to a plus h, which is 1.001. So it's a really tiny interval. And now let's calculate average rate of change over this interval. It will be same thing. So f of 1.001 minus f of 1 over 0.001. So 1.001, I want to plug it into calculator. And my calculator shows the following number, 3.005001. Now I need to subtract 3 and divide this all by 0.001. When I subtract 3, this 3 will cancel, and we have 0.005001. When we divide by 0.001, which means divide by 1/1000, it's like multiplying times 1,000. So this period moves here, and we get 5.001. And as you can see, indeed, the answer is even closer to 5. So we can write it a kind of observation from this numerical experiment. You can write this observation in the same way like you probably write observations to experiments in chemistry or physics. So now I want to do the same. So observation. Observation. As the values of h, which is the lengths of the interval, become smaller and smaller, because we took values like 0.1, 0.01, 0.001. So the average rate of change becomes closer to 5. In fact, approaches 5. Average rate of change approaches 5. Now let me write this observation using mathematical terms and the ideas that we have studied. So when something approaches something, we call it a limit. So limit. Now, limit as h values become smaller and smaller. That means h values approach 0. So this is what we have here. H approaches 0. Now limit of what? Of the average rate of change. What's the formula for average rate of change that we are using? F of a plus h minus f of a over h. So this is the limit that we have that we are observing, and this limit is 5 because the values of the average rate of change, they approach 5. So the limit is 5. So this is what we have observed. This is how our observation can be expressed using mathematical notations. And now this formula is extremely important in mathematics, in calculus and in mathematics in general. It is so extremely important that it has a name, actually several names and several notations in mathematics. The short name is the derivative. So the left-hand side, this limit, the left-hand side of this formula is called the derivative. The right-hand side is just the value. In a different example, it could be something different from 5, so it's not that important. The important part is this limit. And this limit is precisely what is called derivative in mathematics. More precisely, we call it derivative of function f of x, which in our example was x squared plus 3x minus 5 minus 1 at point a or f of a or a equals 1 or x equals 1, because this is what we chose for a equals 1. So derivative of this function at this point. That's one name of this. And now the short notation, I already mentioned there are several names of this expression, and then there are several notations. The name most commonly used and the shortest is the derivative. And the notation, again, the commonly used and the shortest notation is this. We use the same letter like for the function f, but we put a tick next to it and then put a in parentheses. So we read this notation f prime of a. And a doesn't have to be 1, it could be actually any a, so maybe more precisely to say that it is derivative at point x equals a. In our example, a was equal 1, but in a different example it could be any other value, any other point. So this is the common notation, one of several common notations. Very often this common notation used together with the formula itself, and so altogether we get formula for the derivative. So maybe I will write it on the top. Formula for the derivative. F prime of a is the common notation for the derivative, and then the limit. So limit as h approaches 0 of the quotient f of a plus h minus f of a all that over h. Also, oftentimes in this formula, instead of a, we put x, in order to stress that a doesn't have to be constant. Like in our example, a was equal 1. But it doesn't have to be 1, it could be any number. And from that point of view, a is a variable as well. So you can plug in anything for a. And in order to stress that you can plug in anything for a, then we sometimes change this formula to put x instead of a. So we have, I put or, same formula with x. This formula is very little different from, is almost the same as the previous formula, except instead of a, I will put x in order to stress that this a is actually variable, it can vary. So limit as h approaches 0 of f of x plus h minus f of x over h. Once again, this is formula for the derivative.